Okay, we're going to keep talking about recurrence relations. I just wanted to do one more example similar to last time, and then we'll talk about certain types of second order recurrence relations. So last time, in the previous video, we were talking about first order, usually non-homogeneous recurrence relations. Oh, I should add the word here, linear. In other words, we have things which look like this. An is equal to some constant times an minus 1. Let's say the constant could be negative 7, an minus 1, and then plus some function of n. So, for example, we could have here, 3 to the n. And the trick we came up to solve this is to set up a telescoping series, or a telescoping sum. So the way to do that is bring your an minus 1 and your an to the same side. So I'm going to write this as an plus 7 an minus 1. It's amazing what I can do with the technology rather than writing on the board. I can just drag things around. So we bring this to the same side, and we have that it's equal to 3 to the n. Right? And what we basically did is we, take a similar equation for the previous term. So an minus 1 plus 7 an minus 2 equals 3 to the n minus 1, and so on and so forth, down to, let's say, a2 plus 7 a1 is 3 to the 2, or 3 squared, and then a1 plus 7 a0 is 3 to the 1. Okay. By the way, I should say, what are we trying to do here? Let's say I want to find the general solution to this recurrence relation. So the general solution, remember that in the general solution, the idea is all you're given is the initial kind of recurrence definition. You're not given any initial conditions, and you want to find the solution to the recurrence relation with no sort of assumption about the initial conditions. So suppose no one told us what A0 is, and we want to find a formula for AN, and it'll kind of depend on N as well as depending on A0. Okay, so I've written all this stuff down, although this isn't very useful at this point because if I sum this up, it's not going to cancel. So what I want to do is take each line and multiply it by something. So the first line I multiply by negative 7. That's because I want my 7 an minus 1 from the previous line to cancel with the an minus 1 on the next line. And to do that, I need to multiply by negative 7. And of course, what you do to one side of the equality, you have to do to the other side. So I multiply by negative 7. Basically, each term will be multiplied by an appropriate power of negative 7. So I'm going to go quickly through this because we've already done this a few examples, but I think that one will be negative 7 to the n minus 2. This one will be, negative 7 to the n minus 1, and then I've got a negative 7 to the n minus 1. And when you sum this all up, the only thing that survives because of the telescoping is, well, I get something involving a0 at the end, and I get an an at the beginning, and what I end up with is an. You have to be careful about what we're dealing with here with the a0. You have to remember I've got this factor in the front, but if you remember that, you see you've got negative 7 to the n minus 1 times 7 a0, and then on the right side I've got some complicated sum, right? If you think about it, what is this summing? Well, it's kind of like k equals 0 up to, let's say, n minus 1, 3 to the n minus k times 7 to the k. Okay. Now, okay, so at this point, usually we want just a very simple closed form solution. So here we've written, we can solve this to get an, right? So an is equal to negative 7 to the n plus this sum. Now, in some sense, this looks like a formula for an, but we shouldn't be satisfied with this because this is not quite what we wanted. We wanted a closed form solution, but this is still in terms of a sum. So we can keep simplifying this a little bit. Oh, I forgot my A0 here. Right. So basically, our final goal here is to try to simplify the summation. So we've got the sum of from k equals 0 to n minus 1, 3 to the n minus k. Ooh, this should have been a negative 7. My bad. Let's go back to the previous slide and fix that. So this should be a negative 7, and this should be a negative 7. So we've got a negative 7 to the k. Okay, so what I want to do here is use my trusty formula that 1 over 1 minus x is the sum n equals 0 to infinity of x to the n. So how do I do that? So, well, this kind of already almost looks like that, but, well, it's a finite sum, which always seems to happen in these problems. We have a nice formula for the infinite sum, and then the trick, as always, is going to be to write our finite sum as a subtraction of two infinite sums. And to make it look a little bit more like this, we can pull out a 3 to the n, and then what we've got is negative 7 over 3 to the k, because 3 to the negative k is 1/3 to the k, right? That's how exponents work. And that's k from 0 up to n minus 1, which is, of course, the same as, so 3 to the n, we take our infinite sum. So I think of this negative 7 over 3 as being x, and then I get 1 over 1 minus negative 7 over 3 minus negative 7 over 3 to the n, because you think of this as, my kind of x to the n, and then over 1 minus negative 7 over 3. And if you want, you can simplify this a bit, but you don't really have to. This could be your final answer. Sorry, I should clarify what is my final answer. So I still need to kind of substitute this back in. So the general solution is an equals negative 7 to the n, a0 plus 3 to the n. Let's tidy this up a slight bit. So 1 over 10 over 3 minus negative 7 over 3 to the n over 10 over 3. Okay, of course we could simplify this further, but anyway, this is our general solution. Feel free to clean it up and do some algebra, but this is the basic idea. And also, of course, if I wanted to find the particular solution, so the particular solution subject to the initial condition a0 equals, let's say, 4, well, would just be what you get when you plug in a0 equals 4. So to get the particular solution with this initial condition, you just plug in a0 equals 4 and you're done. Okay, so that's just kind of a recap back to what we were doing in the previous video. What I want to talk about now is second order, linear, homogeneous recurrence relations. So second order means that each term depends on two previous terms. So second order just means an depends on an minus 1 and an minus 2. Linear means that it depends on these previous terms in a linear way. So in other words, an is a linear function of the previous terms. So in other words, an is just like c times an minus 1 plus, let's say, d times an minus 2. Well, okay, technically, if it was non-homogeneous, you could have some other function of n here, like we've had in our previous cases for first order things, first order relations. But the fact that it's homogeneous means that when I say homogeneous here, it means that the function f of n in this equation below is just 0. So basically an is just some constant times an minus 1 plus some constant times an minus 2. And we want to figure out how to solve these things. So what I'm going to tell you now is a method for solving these things. Basically, I'm going to give you the answer to, how do you solve these things. But what's not going to be clear is why this method works. And hopefully in the next video, I'll be able to justify why this method is actually correct. But for now, we're just going to see why it works. Okay, suppose I've got a second order linear homogeneous recurrence relation. An is c times an minus 1 plus d times an minus 2. And my question is, what is the general solution? Okay, after we talk about the general solution, we'll also be able to figure out what the particular solution is as well. Okay, well, here's the method. So take your recurrence relation and write it as, well, and come up with something that we're going to call the characteristic equation. So the characteristic equation for this recurrence relation is going to be, you just kind of take x, so it's some polynomial, so I have x squared minus cx minus d equals 0. So to get this, you just start with x squared, you minus c times x and minus d, okay, and then set that equal to 0. You might be able to think of this as like, imagine you take your recurrence relation equation and you bring the things to the other side and you plug in, instead of an, you plug in x squared. Instead of an minus 1, you plug in an x. Instead of an an minus 2, you plug in a 1. Okay? Again, I have, I'm not right now justifying why this is useful, but basically, I want you to just memorize, when you have a second order recurrence relation, this is how you get the characteristic equation. Now, why do we care about this characteristic equation? Well, basically the entire solution to the recurrence relation depends on the roots of the recurrence relation, the characteristic equation. So there's kind of three cases. So case one is that the equation has two distinct real roots. Let's say R1 and R2. So what I suggest with these problems is you write down your characteristic equation, you solve the quadratic, you look at the roots, and if there are two real roots, it turns out, and we'll justify this later hopefully, but your general solution is an equals some constant capital A, R1 to the n, plus B, R2 to the n, for constants A and B in the reals. Okay, so you can just write this down. So solve your characteristic equation, find the roots, and you can just write the general solution is A times R first root to the n plus B times the second root to the n for some constants A and B. So it is really that easy. Case two, so things are a little bit different if you end up having a repeated root, right? So suppose the equation has a double root at R. So in other words, if you factor the characteristic equation, you end up with something like this. And in the first case, to go back to the first case, what we're talking about is that your characteristic equation factors like x minus R1, x minus R2, where R1 is not equal to R2. Okay, back to case two. So if it has a double root, then the general solution is just an equals a r to the n. And this is where it gets a bit weird. So plus b times n times r to the n for some constants, again, for some constants a, b in the reals. And again, this is something, once you solve your characteristic equation, you can just write this down. Now, in some sense, this is related to, well, maybe I won't say what it's related to, but yeah, we'll see why this is the case, hopefully in the next video. Case three, well, if you have a quadratic, I mean, it might have two different real roots, it might have a repeated real root, or it might have no real roots, right? And if it has no real roots, then it has constant complex roots. So you have two, complex roots. And the way that complex numbers work is that these are going to come in a conjugate pair. So the complex roots will be of the form a plus bi and a minus bi. Okay. By the way, it's kind of clear that it has this form because if you think about the quadratic formula, right? Quadratic formula is like, suppose I take my characteristic equation and I apply the quadratic formula. So the roots are c plus or minus the square root of c squared minus 4 times negative d, so plus 4d over 2, right? And basically, you can write down your thing like this, and if the thing under the square root is negative, then you have complex roots. And actually the complex case is not any different really than the first case. So you just end up writing an is equal to a times a plus bi to the n plus b times a minus bi to the n. But this time your a and b might be complex numbers. So in the second case, your a and b are real numbers. Your first case, they're real numbers. In the last case, they might be complex numbers. And this, in any case, this gives you your general solution. So this is actually really easy, right? Let's look at an example. So let's suppose that our recurrence relation is an equals negative 2 an minus 1 plus 3 an minus 2. So our characteristic equation is going to be x squared plus 2x minus 3 is 0. This factors as x plus 3, x minus 1 is 0. So the roots are negative 3 and positive 1. So the general solution, it is this easy. You just write it down, is an equals some capital A times negative 3 to the n plus some capital B times 1 to the n. Of course, 1 to the n is just 1, so it's just a negative 3 to the n plus b. Okay. Now, of course, this is the general solution, and you might be asked to find a specific solution, but that's pretty easy, right? So what's the particular solution for, let's say, a0 is 3 and a1 is 8. Well, you can basically just not even basically, you can completely just take the solution you got for an in general and just plug in n equals 0 and set that equal to 3, plug in n equals 1 and set that equal to 8. By the way, it's worth mentioning here that if you're ever doing a second order recurrence relation, you're always going to be given two initial conditions, right? It's going to be two previous values or two early values in the sequence that you're given as your initial conditions. So, okay, so a0, so we've got that 3 is equal to a0, which is equal to a times negative 3 to the 0, which is 1, plus b, right? So we have the kind of equation a plus b is 3. 8 is a1, which is negative 3a plus b. So negative 3a plus b is 8. Let's say I subtract these equations, so I get 4a. So I'm subtracting the second from the first. 4a is equal to negative 5. So that implies a is negative 5 over 4. And so b is 3 minus negative 5 over 4, so plus 5 over 4 from the first equation, which is 17. So 12 plus 5 is 17 over 4. So b is 17 over 4. Okay, so your final answer then is going to be that if you're asked to find the specific or particular solution, your final answer will be an is negative 5 over 4, negative 3 to the n, plus 17 over 4. Okay, another fun one is the Fibonacci sequence. So remember Fibonacci sequence, it starts with f0 is 1, f1 is 1, and then fn, or am I starting at this at the wrong place? Yeah, I think usually people start this with f1. So f1 is 1, f2 is 1, and then fn equals fn minus 1 plus fn minus 2 for n at least 2. Okay, so probably most of you have heard of the Fibonacci sequence before. Let's see how to get a formula for it. So we start with the recursive definition here, and we can write down the characteristic equation. So it's x squared minus x minus 1 is 0. Now the roots of this equation are going to be, so negative b plus minus whatever, so 1 plus minus the square root of 1, negative 1 squared, which is 1, minus 4 times 1 times negative 1, so plus 4 all over 2. So this is just the quadratic formula. So the roots are 1 plus or minus the square root of 5 over 2. So the general form, the general solution is fn is a times 1 plus root 5 over 2 plus b times 1 minus root 5 over 2 to the n. So these are both to the n. Because this, these are the two roots of the characteristic equation. Okay, so let's solve for a and b by looking at our initial conditions. So by the way, this is the general solution. And now if we want to get the particular solution, we need to use our initial conditions. We need to remember that these initial conditions are for the case n equals 1 and n equals 2. So we have f1 is a 1 plus root 5 over 2 to the power 1. So it's just 1 plus root 5 over 2 plus b times 1 minus root 5 over 2, which is equal to 1 because f1 is 1. And then f2 we can write similarly. So a 1 plus root 5 over 2 squared, b 1 minus root 5 over 2 squared, and that's equal to 1 as well. Okay, so this is a system of equations, and to kind of, you can solve this if you want, but at the end of the day, what it ends up giving you is that a is 1 over root 5, and that b is negative 1 over root 5. Okay, so now you can plug this into your final, you can plug it into your general solution to get the particular solution with the subject to the initial conditions, that nth Fibonacci number is equal to this. Or in other words, it's 1 over root 5 times 1 plus root 5 over 2 to the n minus 1 minus root 5 over 2 to the n. So one of the kind of amazing things about this is that this is always an integer, because the Fibonacci numbers are so clearly integers, right? The first one's an integer, the second one's an integer. Each of the next numbers, fn is always the sum of the previous two numbers. So fn is an integer. But obviously, this formula doesn't look like an integer, right? It's got a whole bunch of root 5s in it. But as it turns out, for every n, if you compute this, all of the square roots will kind of disappear, they'll all cancel, and what you're going to be left with is an integer, magically. Okay, so this is a formula for the nth Fibonacci sequence number. Okay, so a very simple recurrence relation can give you kind of a complicated general form, or a specific, it can give you a kind of complicated formula, basically. Okay, let's look at an example from one of the other cases that I mentioned. So suppose you're given the recurrence relation an equals 8 times an minus 1 minus 16 times an minus 2. So we immediately write down our characteristic equation, x squared minus 8x plus 16 equals 0, and we solve it to get the roots, and we notice that there's a double root at 4. So, and again, it really is this easy to get the general solution. You just write down an is a times 4 to the n plus b times n 4 to the n, okay? This is the general solution. Now suppose we're given the information that a0 is, let's say, 5 and a1 is negative 2, and we want to find the particular solution subject to these initial conditions. So again, like usual, you just plug in a0, which is going to be a times 4 to the 0, which is just a, plus b times n times 4 to the n, which is 0. So it's just a is equal to 5. And so actually that just gives you the value of a. A1, we've got 4 times a plus, so if I plug in a 1 for n here, b times 1 times 4, so it's again 4 times b is negative 2. So now I plug in my value for a, so what I have is 4b is negative 2, a is 5, so I'm subtracting another 20, so it's negative 22. So b is negative 11 over 2. Final answer, an is 5, 4 to the n, minus 11 over 2 times n, 4 to the n, for all n. So this is my particular solution, subject to the initial conditions. Okay, so again, it really is that easy. Let's look at a complex root example. So suppose we're dealing with the recurrence relation an equals 6 an minus 1 minus 13 an minus 2. We write down the characteristic equation, so x squared minus 6x plus 13 is 0. And we go, I can't see the roots of this thing just by looking at it, so we take our handy dandy quadratic equation, and okay, so the roots are 6 plus or minus the square root of 36 minus 4 times 13 over 2, which is going to be equal to 6 plus minus square root of 36 minus 52 over 2. Okay, so we can see we've got a negative number up here. So what we've got is a negative 16, and the way that, complex numbers work is that this is 4 times I, because it's 4 times the square root of negative 1. Square root of negative 1 is I. So our roots are 3 plus or minus 2i. So okay, our general solution is, we can immediately write it down. It's an is a times 3 plus 2i plus b times 3 minus 2i. Oh, to the n. Don't forget the exponents. Okay, now again, let's suppose we've got some initial conditions. So a0 is, let's say, negative 3, and a1 is 10. So we plug it in, and we see what we've got is negative 3 equals a plus b, because when I plug in, a0, if I plug in a 0 for the exponents, I get 1. And then you get 10 is equal to a times 3 plus 2i plus b times 3 plus 3 minus 2i. So let's rewrite this one. So I've got 3 times a plus b plus 2i times a minus b. Now a plus b from the first equation is negative 3. So we get that this is negative 9 plus 2i a minus b. Okay, and now we can see that in order for 10 to be equal to this, well, we're going to need a and b to be complex numbers. Okay, maybe it's not obvious to you, but let's keep solving the equation, and then we'll see what we need a and b to be. Okay, so what we deduced so far is that -3 is a plus b, and that 10 is equal to -9 plus 2i a minus b. Let's solve this for a minus b. So 19 is equal to 2i a minus b. So therefore, a minus b is 19 over 2i. If I multiply this on the top and bottom by I, we get 19i, a negative 19i over 2. Now a minus b is equal to this, and a plus b is -3. Let's add those two equations. So I get that 2a is -3 minus 19i over 2. Divide by 2, a is equal to -3 over 2 minus 19i over 4. So in particular, it's a complex number. And b is supposed to, a plus b is supposed to be -3, so I need b to be -3 over 2 plus 19i over 4. And so my final solution, my final particular solution to this recurrence relation is -3 over 2 minus 19i over 4. I think it was 3 plus 2i to the n, plus -3 over 2 plus 19i over 4, 3 minus 2i to the n. This is just plugging in a and b into the general solution. Yeah, so this is a bit crazy, right? We've got, some sort of thing which is involving a whole bunch of complex numbers. And somehow, no matter what n you put into it, it always ends up equaling an integer. So that's how these things basically go. You find the general solution by looking at the characteristic equation, and then you find a and b by, so if the question just asks for the general solution, you just give them the general solution that you get from the characteristic equation. It's really easy. If it asks for a particular solution, you have to plug in a few kind of specific values and then solve for the a and b. Okay, so that's all I have for this video, and I will see you in the next one. Oh, my green screen is having real troubles. Okay, see you.